I'll begin with a word of prayer. Ahem. 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 Dear Father, we thank you for this day. We thank you for Convo letting out early so we have time to have fun with our friends. Just pray you be with us today. Help us to understand the math we're going over. Just you be glorified again, Lord, in what we do this day, Lord. In your name I pray. Amen. Okay, so, well, I guess just first, I don't know. Okay, so the one problem on the quiz, you have to solve x prime equals to ax, where a is the companion matrix of an irreducible quadratic cubed. I mean, that's a tough problem. And I have a couple of competing ideas. I mean, the first and least inspired way would be just to try to find a complex eigenvector and then solve a minus lambda I times vector equals to that eigenvector, and then that gives me the generalized eigenvector order 2, and then to solve a minus lambda I times that eigenvector equals to another one, and that would give me a chain of generalized eigenvectors, working my way from the eigenvector up to the generalized eigenvector of order 3. Anyway, it's a complex 3 chain you're looking for. I'm not sure that's the best way to do it. That's one way you could try to do it. The other way you could try to do it would be to actually calculate the cube of a minus lambda I for lambda equal to the complex eigenvalue. That would give you the cube of a 6 by 6 complex matrix. If I understand correctly, you should get a one-dimensional null space there. You should be able to find a complex, you should be able to look at the null space of a minus lambda I cubed, find a non-zero vector in there, and that should serve as oh, not cubed, squared. Not the cube. You should look at the square. We should look at the square. The cube, I think, has to be 0. So the square, though, if I look at a minus lambda I squared, I should get something in there that's non-zero. If I take that vector and I multiply by a minus lambda I, I'll get 0. So that makes it an eigenvector. Excuse me. If I multiply by a minus lambda I cubed, then that would give me a 0, which would make the thing in the null space of a plus lambda I squared. I believe that would make that a generalized eigenvector of order 3. Once you find that, then you can multiply that by a minus lambda I, and that will generate the chain from the top down. You could do that. I think that's probably the best way. But it's still a pain because it's a 6 by 6 complex matrix. The other way I can think of solving this problem, which is more adventurous and maybe is the way I'll actually try to do it, is I know how to solve the problem in real Jordan form easily. If the matrix is in real Jordan form, I can write down the solution with a magic formula following much the same approach as I did last class. But the trouble is, if I solve it in that notation, I haven't solved the problem I'm given. I've solved an equivalent problem in a different coordinate system. So then my problem that I face is how to convert the solution in the real Jordan form back to the basis for the companion matrix. So that causes me to face the problem, how do I relate the basis that gives you the companion matrix and the basis that gives you the real Jordan form? So those are the 3 plans of attack I have for that problem, none of which are particularly nice. That's a hard problem. So, any other comments, questions? Yep. By the way, if you solve it in the real Jordan form, I would give you significant partial credit for that problem. If you happen to not solve the problems given, but solve an equivalent but related problem, I would give you significant partial credit. Yeah.
For the structure of the, because all that question asks for is the general solution, right?
Yeah.
So for the structure of that, is it enough to put your eigenvalues into the magic formula, but as complex values, and then just work it out like that with the complex vectors, or should we try to use?
Well, the thing is, you got to find the complex vectors. That's the pain.
Once you've got them.
Yeah, once you've got the complex vectors, you're just looking for 6 real solutions. So you want C1 x1 plus C2 x2 plus C3 x3, and so forth until you get to C6 x6, where x1 through x6 are linearly independent real solutions to that system of 6 differential equations and 6 unknowns. That's our target there. Anyway, obviously this is not a problem I would put in an in-class test, but it's a take-home quiz. And I just gave you till Friday, so that's why I'm telling you these things. There's hope. You can work together too, right? Yeah. seems like a job for Mathematica, by the way, to cube a 6x6 complex matrix and stuff like that, right? Yeah. Or MATLAB, fine. You engineers, your MATLAB, you disgust me. No, sorry. I think you can even get Wolfram Alpha to do it if you're bold enough. Although we're not sure about the results we're getting at the moment, right, Lorenzo? Yeah. Okay, let me go on then. So I was talking about inner product spaces, and I had just given you this grand, glorious monster definition of a bunch of concepts: orthogonality, or orthonormality, orthogonality of subspaces, and so forth. So I wanted to try to prove to you today a number of interesting and fundamental results about orthogonal and orthonormal subsets of an inner product space. So my first question, and I'm going to start with the question, is if S is a subset of V, and let's suppose that V paired with inner product bracket is a real inner product space. All right. And here's the really, S is orthogonal. My question to you is, does that imply that S is linearly independent? Does orthogonality of S imply linear independence of S? What do you guys think? What did it mean for it to be orthogonal? It means that pairwise, the inner product of any two vectors in S, right? This means that if you take V and W, it's 0 for all V and W taken from S. Orthogonality of a set is pairwise orthogonality of all the elements. So what do you guys think? Does it imply linear independence? Votes for. Votes against. The against have it. In a shocking turn of events, let's see here. Because the pesky thing is, 0 times V is equal to 0. You see? So what this means is that 0 is perpendicular to V for all V and V. Or let me state it with X. See, the 0 vector is perpendicular to all vectors. It's orthogonal to all vectors. So orthogonality of a set does not rule out the existence of 0 in there. And if 0 is in the set, by golly, it's surely not linearly independent, right? All it takes is 1 0 in your set and you're linearly dependent, right? So no. Could have 0, right? How about this, though? Question. If S subset of V is orthonormal, then is S linearly independent? What's orthonormality? That means that if you have Vi and you have Vj, you get Kronecker delta Ij for all Vi and Vj in the set S. In other words, the inner product of a vector with another vector is either 0 if they're distinct vectors, or it's just 1. Notice that what this says is that the length of Vi, by the way, the length of Vi is equal to the square root of Vi, right? By definition, that's 1. I mean, square root of 1, which is, by the way, 1. So an orthonormal set is a set of orthogonal vectors which are also all of length 1. And in this case, we actually will be able to prove linear independence of the set. Let me show you the proof of that claim. So let V1, V2, Vk be elements of S, an orthonormal set. In an inner product space V. V is always an inner product space with inner product bracket in this lecture, okay? Let me stop writing that. I'd rather not write it 20 times, okay? So what do we do to prove linear independence? Same thing we always do. Look at a linear combination, set it equal to 0. What's our goal then? Suppose C1v1 plus C2v2 plus plus CKvk is equal to 0. My goal, of course, is to show that all the coefficients are 0, right? So what you do is you just take the inner product of this with just pick one, you know. So basically, we calculate. Take inner product with, say, Vj. So you get C1v1 plus plus CKvk with Vj. That's equal to 0 inner product with Vj. By the way, that's equal to 0. Inner product is 0. Vector with anything else is 0. You can prove that from the axioms pretty easily, as I talked about last time. Now, what are the properties of the inner product? We have linearity in the first slot, right? So I can break up that sum in the first slot to a sum of inner products, right? So by the axioms we went over last time, C1, V1, Vj, Eventually we get to Cj, Vj, Vj, plus plus Ck, Vk with Vj, equal to 0. Right? Again, bilinearity in the first slot. You guys with me? So, well, that's cool because all of those are 0 except for one, right? This is 0. This is 0. The only thing that's not 0 is this one, right? This is 1 by our supposed orthonormality. And therefore, Cj is equal to 0, but j is arbitrary, right? Hence, C1 equals 0, all the way to Ck is equal to 0. And we find S is linearly independent. So orthonormality does imply linear independence. By the way, how would you fix my original statement to get to obtain linear independence for an orthogonal set? The same argument works, right? If you have orthogonality, what the difference would be, instead of coming out to 1, this would come out to like something else. It could be 3, 4, whatever, some number, right? Provided that you know that your vector is non-zero. So basically all you need to fix my original question is say, well, yeah, that is true. Orthogonal implies linear independence if we say orthogonal, S is a set of orthogonal, and then we have to insert non-zero vectors. See, that's all that we were missing. This counterexample we had is in fact the only counterexample. Orthogonality does imply linear independence if we have non-zero vectors. Is that good? Well, anyway, there it is. Now, I should mention to you, if we have an orthonormal basis, it's so very simple. Let's talk about orthonormal basis calculations for just a second. If beta v1 vn is orthonormal basis for v, and x is an element of v, then x is equal to a sum, all right, j equals 1 to n of the inner product of x with vj, vj. Which means what, thus? The coordinate vector of x with respect to the beta basis is just equal to what? X with v1, x inner product with v2, all the way down to x inner product with vn. The proof of this is like not hard, right? Let x equals to the sum I equals 1 to n of, let's say, ci vi. Why can I do that? If x is in the vector space and beta is a basis, right? Any vector is in the span. And then what do? It's almost the same as the proof I just went through. I'm just doing it in the summation notation now. Consider the inner product of x with vj. So like x vj is equal to inner product of the sum I equals 1 to n ci vi, comma, vj. Right? But I can use linearity in the first slot to pull the sum out and to pull the constants out. And what am I left with? Right? But we assumed orthonormality, right? Which means that the inner product of vi with vj is just Kronecker delta ij, which is the natural enemy of the finite sum, right? It kills all but one term in this sum. What does it leave us with? I equals to j, right? Everything else is 0, so we get cj. But that's exactly what I was trying to prove, is that I mean, I have it with I instead of j. I can fix it if you'd like, but I'll behave. That's the same. Do you understand what this means? If we have an orthonormal set and you want to calculate the coordinate vectors, right, with respect to an orthonormal basis, all you have to do is take these inner products, basically take dot products, generalized dot products, with respect to the basis, and that gives you coordinates. How did you find coordinates before? The correct answer is with considerably more suffering, right? So orthonormal basis is super easy to find coordinates for. You just have to take these inner products. It's not bad at all. All right. Now you probably need an example to make that make sense to you. Let's see here. And so, any question or comment, concern? Oh, I should probably not allow comments. I'll regret that. Let's see here. Let's see here. For example, if I look at beta equals to, let's see here, 1 over the square root of 2, 1, 1, 1 over the square root of 2, 1 minus 1, right? So this is my v1, this is my v2. You can check that, in fact, that is an orthonormal basis, all right? for R2. So if I wanted to calculate what is the, if I say, you know, x equals to 3 comma 2, then say find x beta, what do I do? You can just work, I mean, it's literally x dot v1, x dot v2. The inner product here, of course, is just the dot product. We're in R2. And you can work those out in your head, right? Like 3, 2 dot that is what? 5 over root 2. And this one is 1 over root 2. And you can check, right? Is it the case that 3, 2, is that really equal to 5 over root 2 times v1 plus 1 over root 2 times v2? Is that true? I get 6 over root 2 squared, which is 3 for the first component when I work it out in my head. And if I work out the second component, I get, let's see here, v2, 1/2, what? Uh-oh. Uno momento. What? 3. 1 over root 2 times v2. Oh, sorry, I got to add both of them, right? 4 over root 2 squared, which is otherwise known as 2. Yeah, okay. It's right. Now, there's a question you should ask, though, right? Well, that's great. You just pulled an orthonormal basis from the clear blue sky. How did you find an orthonormal basis for, how did you find an orthonormal basis for R2, right? For R2, it's pretty simple, actually. How to construct an orthonormal basis. How to for R2. All right, you guys give me a vector. Audience, any vector you want, except for 0.
Pi e.
Pi e, I'll take it. So v1 tilde is pi e. So I take your pi e, and I replace it with v1, which is 1 over the square root of pi squared plus e squared, pi e. See what I did? This is called normalizing, right? First of all, I rescaled it to have length 1. There's the first thing in my basis. And then I just need something which is perpendicular to that. Well, for two vectors, I can tell you what it is. You rotate by 90 degrees, rotate by 90 degrees. Pragmatically, you just flip the x, y components and slap a minus on one of them. So all I'm doing is like, this is v1. So v2 is either this guy or that guy, really. So I mean, you could put plus or minus here, and it'd still work. There you go. That's an orthonormal basis, starting with your delightfully random example of pi e. We can play this game for any non-zero vector. You normalize it, switch the x and y components, slap a minus on it, you add an orthonormal basis for R2. How do you do it for R3? How about R3? So you guys give me 2 vectors. I'm gonna start. Suppose we had started with 1, 1, 1, and v2 was 2, 0, 2, right? Clearly, those are linearly independent. Also, they're clearly not orthogonal, much less orthonormal, right? How can you take those and create another set of vectors which spans the same space, right? Let me call these v. We call this Yeah, okay. So let W equal to the span of V1, V2. Here's our goal. Find orthonormal basis for W. So I want to walk you through this. I think the first step we should all appreciate and not be too surprised with. And let's call this orthonormal basis U1, U2, okay? We're looking for beta equals to say U1, U2, where these are orthonormal. It's an orthonormal basis, all right? So U1, well, U1, that's obvious what I'm going to do. That's 1 over root 3, right? 1, 1, 1. I normalized the first vector. There's 1 down. I just got 1 more to go. I can't use my trick from 2 dimensions. That's no longer legit, right? I can't just put a minus and flip. That ain't going to do it. So what I got to do is I'm going to say U2 tilde. All right, what's it going to be? It's going to be V2. All right? And let me try to draw a picture to explain to you what's going on here. So V2 looks like this, right? And then maybe this is V1, right? And along V1, there's the U1 vector, unit vector, like that maybe. This is not the scale. What I want is I just want the part of V1, V2 rather, which is perpendicular to V1, right? What I want, man, what I want is I want to sort of find, okay, there's like this vector, right? And then there's this vector. I can take these two, and I can now this one on the one that lines up with V1. What is that? This one is going to be exactly V1 dot U1 times U1. That's what's going on here. I'm breaking x, like the component in the V1 direction is just the inner product of x with V1, right? That gives me the component of x in the V1 direction. In the same sense, V1 dot U1 gives me the component of V1 in the U1 direction. I meant V2, sorry. If you're confused, that's good because I'm also confused. That's supposed to be V2, 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 V2. 2, dos. So basically the part of V2 that lines up with V1 is this. That's the vector projection of V2 into the V1 direction. Listen, U1 is actually what I called in the previous lecture, what? V1 hat, right? So V2 is what? It's this thing plus this other piece, which you might call the, I don't know what you want to call this thing. It's the orthogonal projection, it's the orthogonal piece of V2 with respect to the V1 direction. The orthogonal projection of V2 in the V1 direction. It's the part of V2 which is orthogonal to V1. You could call it orth V1. That's what I want here, right? As a starting point. I mean, I really want orth. I want something which is orthogonal to V. Sorry, man, like that. But you can see from this little triangle up here what the formula is for it, right? This guy, V2.U1, U1, plus the orthogonal piece should be equal to V2. So the formula for orth V1 sub V1, V2 is nothing more than V2 minus the parallel piece, which is V2.U1, U1. There's no reason that this would be a unit vector, right? It's going to be orthogonal to my first vector, but it won't necessarily be normalized. Let's see here. What's that actually look like numerically for my example? This is what 202 minus, let's see here. What's V2.U1? I'm going to bring out there's a third. I'm going to bring out the root 3. There's 2 of those in here. V2.U1 is 4. And then U1 was 1, 1, 1. So I just took the 1 over root 3, 1 over root 3, and multiplied them like that. And so there you have it. This is 6/3 minus 4/3, 2/3, minus 4/3, 2/3 again. When normalizing a vector, you pull fractions out because you don't want to, I mean, come on, just pull the fraction out, make your life easier. So this is nothing more than 2/3 times 1 minus 2, 1. By the way, at this point, it becomes obvious that that vector, right? Is it clear to you guys that this vector is in fact perpendicular to that one? Look at the dot product of those two. It's 0, right? If you can see it. And so, therefore, we normalize u2 tilde to give us u2, which is going to be 1 over the square root of 1 plus 4 plus square root of 6, 1 minus 2, 1. This procedure I'm using has a name. This is the so-called Gram-Schmidt procedure. The Gram-Schmidt algorithm, as it's often called, gives us a systematic way of taking a given linearly independent set in an inner product space and feeding it through an algorithm which then outputs an orthonormal set. Let me repeat that. You can take any linearly independent subset of an inner product space, a real inner product space, feed it through the Gram-Schmidt algorithm, and you will produce an orthonormal set. It's almost too good to be true, isn't it? So do you guys see how we did that here? Now, how would you get an orthonormal basis for R3 from this, let's say? Continuing this example, how would you find an orthonormal basis for R3? Can we extend beta equals to, what was it? 1 over root 3, 1, 1, 1, comma, 1 over root 6, 1 minus 2, 1. Can we extend this? Can we union this with some other vector, say v3, so that, I guess I shouldn't call this beta anymore. This is what? This is gamma, I guess. I don't know, whatever. It's beta union another vector. Can we extend to gamma to this orthonormal? There are two ways I know to do this. The one is just to run Gram-Schmidt. But on what? You know, you got to find something that's not already in the span of V1 and V2. Can you guys tell me something that's not in the span of V1 and V2? One, two, three. Can you tell me something simpler that's not in the span? Let's be lazier. How about E3? Is E3 in the span? How about E1? Is 1, 0, 0 in the span here? I don't think there's a way you can get 1, 0, 0 from taking a linear combination of these, because in the process of canceling out this, you'll automatically introduce a second component. Like, you can't just get a first component or a third component. I think both E1 and E3 are not in the span. So if I use, basically just run Gram-Schmidt on beta unioned, let's say, 1, 0, 0, that ought to do it. And so the way that goes, let's call this thing V3. So first of all, since we've already done the work, we already have, Gram-Schmidt is kind of stupid if you feed it an orthonormal, like, so like basically we have, okay, so U1 and U2 already done, right? So the algorithm is just like stupid, it doesn't do anything. It's just like, okay, if you subtract off the piece of U2 which is perpendicular to which is parallel to U1, it's nothing. So it's already been perpendicularized. how about U3? Well, U3 tilde is going to be the following. U3 tilde, what it's going to be is V3 minus V3 dot U1, or you could make it, I mean, the order of the terms doesn't matter here, okay? So if you have three vectors, then you subtract off the piece which is parallel to the first one and the piece which is parallel to the second one. This will give you a vector which is perpendicular to U1, U2, and is in the direction, at least partly in the direction of V3. So this will give you, let's see here. I said V3, 1, 0, 0. What's V3 dot U1? 1 over, yeah, don't die. Thank you. I'll try not to. 1, 1, thank you, that's very kind. U2 minus 1/6. What's V3 dot U2? That's just going to be a 1 again. Oh, this is rather boring. And so what do you got? U3 tilde. What's 1 minus a third minus a sixth? Is that a half? What's a third minus 2/3? Minus a half? Do you guys agree? All right. So factor out a sixth, and you got yourself a 3, a minus 4, and a minus 3 again. And so normalizing that is easy. U3 is 1 over the square root of 9 plus 9 is 18. Fine, 9 plus 16, I won't try to do it in my head. 9 plus 16 plus 9 again, whatever that is. 3 minus 4, 3. In other words, U3 is 1 over the square root of 34. 3 minus 4, 3. That has length 1. Yep.
Should the second term be 0? Minus 1/3 minus negative 2/6?
Well, we can check our answer, right? If the dot product of this and that is not 0, I'm very much on the favor of your comment. Let's see here. 3 plus 8 plus 3 is not 0. All right. I will now take your comment more seriously. What was wrong? Is arithmetic, right? Yes, algebra.
The algebra thing. So 0 minus 1/3 minus negative 2/6. So minus 1/3 plus 1/3 is 0.
Oh, thank you. Thank you, thank you, thank you. I much prefer to have a 0 there because that puts a half out here and a 1 and a minus 1. And I should have just guessed this from the outset. I mean, you know, if you're tasked with the problem of finding orthonormal basis, if you can see it, then good, right? Now that, I think you can see is immediately, obviously, perpendicular to U2, and it is perpendicular to U1, right? And it's length 1. So there you have it. This is an orthonormal basis, which we just built from extending the orthonormal basis for the subspace W to the whole space by just guessing a point outside the subspace. Now, yes, the arithmetic is easy to mess up. I sent you guys a link, I believe, to a calculator which actually does Gram-Schmidt for you. So there's, you know, and by the way, I've just showed you Gram-Schmidt for Rn. How does Gram-Schmidt work for inner product space? Like, I should at least start that. So what's the general algorithm? I won't try to tell you the whole thing, but it's something like this. Given S, which is equal to, say, V1, V2, Vk. Step 1 is we just say U1 is equal to, and this has to be linearly independent. If it's not linearly independent, I don't know what's going to happen. So you define u1 simply to be 1 over the length of v1 times v1. In other words, you define u1 to be v1 hat. That's the first step in the algorithm. Step 2 is, I call it u2 tilde as an intermediate step. u2 tilde, what it's going to be is simply v2 minus, all right, and now I'm in inner product space, so I can't use dot products. Doesn't make sense. But you just replace the dot products with inner products. The same story goes. So you do v2 minus the inner product of like v2 with u1, u1. You can prove that u2, I mean, there's a claim here. It's an easy claim to prove, is that u2 tilde with u1 is equal to 0. So it's orthogonal to u1. And then what do? Well, u1, rather u2, u2, you normalize it. u2 is equal to u2 tilde. Put a hat on it. To be specific, you 1 over the length of u2 tilde times u2 tilde. There you go, that's u2 tilde. How do we construct u3? u3 is equal to v3 minus the inner product of v3 with u1 minus the inner product of v3 with u2. This is not u3, this is u3 tilde, because it may not have length 1. You can in fact show that u3 tilde is perpendicular to u1 and u2. That is actually following from this formula. I explain in the notes basically that you could think of u3 tilde as being equal, what it is you're basically doing what you're doing is you're doing orth u1 of orth u2 of v3. I mean, I look at it that way. It's a composition of the orthogonal operator over and over and over again, one for each vector, each time orthogonalizing with respect to the operator. And what pops out of that formula is this v3 minus the inner products of the appropriate previous vectors. And if you just keep doing this, you obtain an orthonormal set.
What's the subscript on the orthonormal?
Which one? Oh, here?
Yeah.
u1 and u2. So I'm not going to prove to you that this works, but that's how it works. Okay, so that gives us wonderful theorems. For example, given an inner product space, in fact, given any subspace of an inner product space, there exists an orthonormal basis. Why? Well, take a basis for your subspace, right? If it's not already orthonormal, do what to it? Run it through the Gram-Schmidt algorithm, and out pops an orthonormal basis. So without loss of generality, we can always assume that we have an orthonormal basis to work with, which is very nice, as I was trying to explain to you, both in terms of the coordinate vector and in terms of explicit calculation. All right. Another little theorem. If W1, well, let's say this. W1, W2 subspaces of V, then W1 is perpendicular to W2 if and only if there exists basis beta 1 and beta 2 for beta 1, for W1 and W2 respective. Such that what? So what I'm trying to say is, if you can find a basis for two subspaces such that the bases are orthogonal, it implies that the whole space is orthogonal. So that's a result which is known. Man. All right. I think I'll just prove this direction today. So suppose W1, is perp to W2, right? If beta 1 equals to, say, xi, and beta 2 equal to, say, yj, are bases for W1 and W2, then what? Then the inner product of xi with yj, it's kind of stupid. I mean, is equal to 0 since xi is an element of W1 and yj is an element. I mean, I'm sorry, this is too embarrassing to even write down. I don't know. I mean, whatever. I mean, if they're perpendicular subspaces, that means that every pair of vectors that you take one from one and one from the other, it works out to inner product 0, right? So, of course, the bases have to be perpendicular. I guess the more interesting direction to the proof is the other implication, right? Fine, I'll do the other implication. I mean, that was kind of a non-event. I should have done the interesting one. So if you have beta 1 is perpendicular to beta 2, which means that these are orthogonal sets in the sense that any two pair of vectors, one from beta 1 and one from beta 2, inner products to 0, all right? And the span beta 1 equals to W1, and the span of beta 2 equals to W2, all right? So suppose they're bases in particular. Let x equal to, say, a sum of xi. I'm sorry, I was using xi as the basis up there. I'm going to change notation here. I hope you're okay with it. I'm sorry. X equal to that, all right? And let y equals to this. Let's say wj. Sorry about my notation in the first half of this proof. It's really bizarre. Not my typical notation. I should probably just cross it out. Oh well. So these two vectors, what happens when you take the inner product of them? Well, you can pull the sums out by the linearity of the first slot and the second slot. So I equals 1 to the dimension of W1, and the sum j equals 1 to the dimension of W2. And our coefficients were x sub I and y sub j, and I have the inner product of vi with wj. But I'm assuming that the bases for the subspaces are perpendicular, right? So we know that the inner products I just wrote are all 0. So by assumption, this is 0. So this is equal to 0. But x and y were arbitrary, so that implies that the subspaces W1 and W2 are perpendicular. Es bueno? All right, so what's the thing I proved at the end of last class? I proved that the perp to a given set was a subspace, right? So there's other theorems we can prove about that. I should continue that discussion. So here's further properties of the perp. So last time I proved for you that if S was a subset of an inner product space V, then the perp of S is a subspace of V, right? But there's more. What happens if you take the perp of the perp? We proved this last time. We also, in fact, can prove that the perp of the perp, well, I would say it's S again, but the thing about this S was it was possibly a finite set, right? In fact, I'm not assuming that S is a subspace at the moment. It's a set of vectors. So what you get back, well, the perp is a subspace, right? So what vector, it has to give you back a subspace again. What subspace does it give you? Well, it just gives you back the span of S is all it is, okay? So basically, you find your way back to the span of the set of vectors you started with. Now, this is particularly simple if you have a subspace. If you have W, which is a subspace of V, then the perp just goes back where you started again, if you do it two times. But there's more. There's more. You can, in fact, show that W, direct sum, W perp, is equal to the whole vector space. In other words, W and its perpendicular space are complementary. Complementary subspaces are ones whose direct sum forms the whole space. The proof of this basically involves using the tools we've developed today. This notion of an orthonormal basis, the idea that you can build coordinates from an orthonormal basis basically with projections based on inner products, all of that comes into play in the proof of that, and that's what I'll show you next time. I'm going to show you this, and I'm also going to show you how that immediately leads us to a few theorems. In particular, I'll mention next time I'll also develop how you build the perpendicular space using column operations for Rn. And finally, that will lead us to sort of the crowning jewel of this study, which is the method of least squares, which will give us a method to solve linear equations that can't be solved. Right, so if your linear system is inconsistent, right? In other words, if you're trying to solve AV equals to B, and B is not an element of the column space of A, it turns out, and I'll explain why this is, that A transpose AV equals to A transpose B does have a solution, and the solution to this problem is the best approximation to the original problem if we view it in terms of projections of the original problem. It's an approximate solution. It's not a solution, of course, but it's the best approximation. And that is all built over the theory of orthogonal projections that we're trying to develop.